Okay. So good morning. We're going to be talking about tensions, and a tension is a pulling force usually in a string or cord. So if I have an object here and I have a cord attached to it, then we can take that cord and pull on it, and we get a tension. Now, let's say that that cord is also attached to the ceiling or something like that. Then the cord will display Newton's third law by pulling with reaction pair on the ceiling. So what the cord really does is to essentially separate the action-reaction pair physically. So that instead of being close contact between the two objects, now it's going to be at a distance transmitted through the cord. So notice that here is the free body diagram for the ceiling. And here's the free body diagram for the object. And we have the two tensions. Like so. Now what about the cord itself? What if I looked at the free body diagram for the cord? Well, if I look at the cord itself, here's my cord, then I've got one tension pulling this way, and I've got another tension pulling this way, and those tensions cancel each other out. So that I end up with a net zero force on the cord, but it's really two different tensions here. So if I were to break this cord and place a force meter inside here, so this is going to be some kind of force measuring device like a spring scale, then the spring scale would read T and not 2T. Now let's think about this. Why does that work? Well, consider the spring scale by itself. The spring scale is designed so that if you put a weight on it like that, then it pulls down, right? But what is happening at the other end of that spring scale? Because the spring scale is not accelerating, we know that there is a net force.
Teachers, pardon the interruption.
Okay, so notice that the spring scale is calibrated so that when it experiences equal but opposite force on each side, it registers Fg, that force. So just be careful as you're thinking about problems with tensions and spring scales, what's being read there. It's assumed that we're going to have equal but opposite force on each side. Now, this is true for a massless cord. And it is also, we're going to see later on that we also have to consider whether or not we're going to have to consider cords passing over pulleys and whether or not there's any frictional force involved with pulley, right? What if my cord is a real rope, so it actually has real mass to it? Well, in that case, when I pull on a real rope, and I don't think there are any problems in a book like this, but I'm just going to briefly talk about it. If I have a real rope of mass M that is attached to some object, it's going to be pulling with a tension T1 and then T2, then it's entirely possible that we can have different tensions on either side, and the difference in tensions, T2 minus T1, will equal the mass of the rope times the acceleration of the rope. If my rope is massless, notice that we would use 0 for M, in which case we would get T2 minus T1 is 0, or T1 equals T2. So a massless rope must always transmit 100% of the force through it. T on one end will be equal to T on the other end, regardless of its acceleration. A rope with actual mass, not so. It's going to experience a difference in tensions that is proportional to its acceleration. Does that make sense? Now, what kinds of mass are we talking about? Like for lab strings, we're talking about fractions of a gram. So, in terms of the whole system, the mass of chords is almost always negligible. Okay, that's the theory. Now, here's how this all works out in practice. Let's take a look at this system right here. We're going to have an object that has a mass of 10 kilograms, and it's going to be suspended from the ceiling by two different cords that have been tied rather inexpertly. So that one of them makes a 30-degree angle with the object, and one of them makes a 60-degree angle with the object. Really what we're talking about is a 60-degree angle and a 30-degree angle with the ceiling. Notice that if we assume that the object is parallel to the ceiling, the top of the object is parallel to the ceiling, the classic geometry thing, parallel lines cut by a transversal alternate interior angles are congruent. Or the classic Z. Yeah? I always imagined myself as Zorro in geometry class. And so the question now is, what is the tension Okay. What is the tension in each chord? All right. Now, we want to break this up into two pieces. The first piece is the physics piece, and the physics piece is not very hard. And then the second piece is going to be the algebra piece where we solve the equations that we get. I want you to focus on the physics part, but we also have to be skilled with doing the algebra. So what I'm going to do is to set up the equations, and the basic principle for setting up the equations is count your variables. And then when we solve, we're going to have a couple of different methods that I'll show you for solving. One of those is going to be solving by substitution or elimination by hand, and the other is going to be setting it up as a matrix equation and solving it by calculator. Okay? So that's our plan. Physics, then algebra. And we'll just walk through the whole thing. Okay, so to do the physics, the basic plan is x and y components separately. What happens in the x stays in the x, what happens in the y stays in the y. And so to do that, I'm going to represent my object here with all of the forces acting on the object. And the first force, of course, is the force of gravity, which is going to be equal to mg, or in this case, 100 newtons. Okay. And the second force is this guy right here, which is T1. And the third force is going to be T2. Okay? This is the official free body diagram. And what I'm going to encourage you to do, and I've never done this with students before, but what I'm going to encourage you to do is to take this free body diagram, and once you've done it correctly, showing all the forces acting on it, bronze it. Don't change it. And here's one. We're about to split T1 and T2 into components in the x and y direction. AP exams got really picky about what they will accept and what they won't accept for free body diagrams. And in particular, they were really fussy about how components could show up. And the reason for that is that they had a large number of students that were taking forces like T2, and then they were breaking T2 into components like this, and leaving all of them there on the diagram. And what that does is it effectively doubles the force. because I now have T2 and I have these T2x.
So they wouldn't cross out T2.
Right, so for a couple of years, they said, you can have the components, but you have to cross them out. Then they got even pickier and said, we're not even going to accept that anymore. So, this is going to be your free body diagram showing the forces. Once you've done that, then we're going to get ourselves a working free body diagram that's going to show T2x and T2y here, and T1y and T1x. Okay? So we're just going to do that to avoid any potential problems with our AP grading. It's a little silly, but it's not horrible, because, you know, to give them credit, this original free body diagram does show what's actually going on. This is a bookkeeping or accounting trick that you're using. Yes?
So we should do the second one?
No, you're going to do both.
Oh, both.
This is your free body, this is your official free body diagram. This is your working FBD that we're going to use for computation purposes. Okay? And now we'll do the usual component thing. This guy is going to be T1 sine 30 degrees. This is going to be T1 cosine 30 degrees. This is going to be T1 sine 60 degrees. And this will be, that's, yep. These are T's. There we go. That is definitely not recommended practice. And this will be T1 cosine 60 degrees. Now I want you to notice we still have only magnitudes here. We don't have any direction signs on this yet. We're about to fix that over here. So, working free body diagram. And then we're going to follow that up with sum of forces in the x direction and sum of forces in the y direction as two separate equations. Yes, sir. Great question. Okay. This is a matter of taste, and you can do one of two things. There is an always due east method, and it has its pluses and its minuses. Pun sort of intended. And there is going to be the given angle method. And it has its pluses and minuses also. If I use the given angle method, where I use the 60-degree angle because it's given to me, then I'm going to use SOHCAHTOA to figure out values of components, and I'm going to use common sense to figure out direction signs. Specifically, I'm going to read the direction from the arrows. So in this particular case, I have a T1, was it? Yep, a T1 that's pointing backwards, and it makes an angle at 60 degrees from due west. So that when I draw the components, the values of those components, T1x and T1y, can be found from T1 by recognizing that T1x is adjacent to my 60-degree angle, and therefore T1x is going to be equal to T1 cosine 60 degrees because adjacent. And when I put it into the equation, I will recognize that it's pointing west, so I will put it into the equation as a negative quantity. So that's the given angle method. The advantage of the given angle method is that I don't have to figure out crazy angles in weird quadrants. So that's a thing. If I had, for some reason, a T3 that was at an angle relative to due south of 30 degrees, then I would again draw my components, and this time I would recognize that T3x is opposite the 30-degree angle, so it would be a sine component. regardless of the fact that it's labeled X. Okay? So we're just thinking opposite or adjacent. There's another advantage to this. When we start doing problems on ramps, then we're going to end up with angles that are measured from due south. And so it will be convenient for us to use the given angle method.
Good old E59 now.
Please disregard that. Okay. So now, the always due east method is what you have in mind, and actually mathematically, I prefer that.
Teachers, please disregard that.
Okay. The always due east method is, given a particular angle, I am going to normalize it to due east. And I'm going to do that by taking this angle right here and saying, okay, if I would measure it from due east, what do I get? And the answer is a 120-degree angle. When I do the always due east method, then my x component is identically the cosine component. And the y component is always the sine component for angles measured from due east, because I'm putting the whole thing on a unit circle and I'm saying what's the angle. And furthermore, when I put those angles into the unit circle, I will always add. And I will let the cosine and sine take care of the negative signs. This is the way a mathematician thinks about these problems. This is basically the way a physicist thinks about these problems, or an engineer. And I don't care which one you want to be, just pick a method, and for that problem, stick to it. Does that make sense? So, I will show you the setup for this problem. I'll show you the setup of it. Using, this is our given angle method, and so using this plus shifted, we're going to come back to the sum of forces in the x direction, and we are going to take only the horizontal angles, arrows, only the horizontal components as forces in the x direction. T1x is pointing to the left, and so we're going to mark that as a negative T1 cosine 60 degrees, which is root 3 over 2. And T2x is going to be in positive direction. That's T2 cosine, I'm wrong, this is 1/2. And cosine 30 degrees is root 3 over 2. And all of that now adds up to 0 because it adds up to the mass times acceleration of the block, and the acceleration is 0 because the block is sitting there. And then we can appeal to the calculator to get various decimal values. This is minus 0.5 T1 plus 0.86 T2 equals 0. When I do the same thing in the y direction, I want you to consider only my vertical arrows here, like that. And so, since T1y and T2y are both in the upwards direction, that will be positive. And so we have T1 sine 60 degrees plus T2 cosine sine 30 degrees. There we go. Minus 100 newtons, and that equals 0 also. Or when I write this out, I get 0.866 T1, 1.5 T2, and I usually add the constant 100 signs. How are we doing for the setup? Does this make sense to everybody?
Yes.
Okay. Well, if we had taken the always due east method, then what would have changed was only here and here we would have had, our setup would have looked like this, Sum of forces in the x direction would be T1 cosine of 120 degrees plus T2 cosine of 30 degrees equals 0. And when we actually get those numbers turn out to be negative 0.5 and 0.866. So that the decimal equivalents for both methods always give the same equations. And in the y direction, we would have done T1 sine 120 plus T2 sine 30 plus 100 newtons sine 270 equals 0. And that gives us, again, 0.866 T1 plus 0.5 T2 minus 100 equals 0. So again, we get the same decimal equivalent.
Oh, this is
The always do east, yeah, always do east method. I've gone back and forth in my life on which one I like better.
What do you like better now?
I kind of like the given angle method, but if I got to keep my head straight,
Yeah.
I go back to the always do east. Okay, so that's the physics, and we've done it in slow motion here. But honestly, once you're used to reading free body diagrams, you guys may probably remember from last year, that process goes pretty fast. Now, what about the solving process? I want to give you some options here. We have these two equations. Which way you're going to choose to solve it, we are always going to set up our equations in what I call standard form. Standard form is going to have the variables lined up under each other. And the constants on the right. Now, that's not because it's a mathematical necessity. It's because for human beings, it's a bookkeeping necessity so that we can cut down on the stupid errors. Okay? Now we're going to choose among three options: substitution, elimination, or calculator matrix. Substitution is indicated only when it is easy to solve for one variable in terms of another. This is one such instance. Notice that I've got something T1 plus something T2 equals 0, so it's fairly easy to get T1 equals something T2 and plug in. Elimination is going to be indicated when I have a relatively small number of variables, 1, 2, or 3, and I can eliminate the variables fairly easily. And calculator or matrix is going to be indicated when you have large numbers of variables, and that's usually the case in real-life systems. So this is the way that professionals do it most of the time these days when they're solving real-world problems with large numbers of forces. Okay. Well, let me just show how this works. To do substitution, we're going to solve for T1 in terms of T2. We're going to substitute into the other equation. Yes? The sum of forces in the y direction was 0, but one of those forces was the 100 newtons pulling straight down. Yeah. Yeah, what he said. Really? So, if we solve for T1 and substitute, it might look something like this. Subtract 0.866 T2 from both sides. Divide both sides by negative 0.5 and get 1.732. So, and now substitute into the second equation right here. And when you do, something lovely happens. I'll let you work out the math on this, but 0.866 times 1.732 just happens to equal 1.5. So that we get 2.0 T2 is equal to 100 newtons, and T2 is equal to 50 newtons. And since T2 is equal to 50 newtons, we can come back and substitute in here. And when we do, we get, well, it's 5, so it's B 6.6, 87 newtons. Force there. The reason that I knew that would happen, actually, just to give you this is a total engineering thing, but notice how these two angles are complementary to each other. That means the sine of one equals the cosine of the other, and vice versa, so that when I do the substitution, I end up getting a sine squared plus cosine squared kind of a thing. So the substitution process involves solving for one variable and plugging it into the other equation. Warning! If you solve for one variable and plug it back into the same equation, you will discover that 0 equals 0. Always true, never helpful. So the substitution has to occur into a different equation than the one that you solved to begin with. Okay, how does the elimination go? The elimination is going to proceed by taking our equations and targeting a variable to eliminate. If you've got 3 equations, it would make sense to target a variable that only shows up in 2 of them to eliminate. If you have 3 equations and you've got a variable that only shows up in 1 of them, then you might want to consider substitution for possibility. Okay? And so having targeted a variable to eliminate, here I'm going to target T1 because we have opposite coefficients. Right? Then you're simply going to multiply the top one by the coefficient here, and the bottom one by the coefficient here. Really the opposite of the coefficient right here. So that when I add, I will have equal but opposite coefficients here that will cancel and give me 0. Now when I do, here, 0.866 times 0.866, root 3 over 2 times root 3 over 2 is 3 over 4. And so I get negative 0.343 T1 plus 0.75 T2 equals 0. That is supposed to be an arrow. There we go. And here I get positive 0.433 T1 plus 0.25 T2 equals 50. Notice that I have to check that these guys are equal to opposite. They add up to 0, and I get, there's my coincidence again. So that I get T2 is equal to 50 newtons, and then I can plug that value of 50 newtons back into either equation, and I will find in both cases that T1 is 87. And that's good. how do I check this? Let me take a break to talk about checking this, and I think we can do matrix solutions tomorrow, given our lack of time. When I do a check, I always check by going back into the free body diagram, the working free body diagram, and verifying that everything checks out. Take your 50 newtons, get your sine and cosine components here, and when you do, 50 newtons times the cosine of 30 degrees is going to be equal to 43.3 newtons, and T2y times cosine of 30 is going to be 25 newtons, so. And T1y, 87 times cosine of the sine of 60, is 75 newtons, 75.3 newtons. And T1x is going to be 87 times the cosine of 30.
43.
I'm sorry, the cosine of 60, right? We hope it's that, which is 43.5.
Close enough.
Right, exactly, close enough. So that I can now visually verify that 25 plus 75 cancels 100, and 43.5 and 43.3 cancel each other out. There's a little bit of
At a rounding error.
rounding issues.
And we're
And
basing
then,
it.
exactly, that's right. So my check is a physical check. I don't go back and check the equations. What happens if my check fails? If my check fails, there are two possibilities. One is the physics is wrong, the other is the algebra is wrong. To sort those two possibilities, I would then take my solution here, and I would go back to the original equations and just plug in and verify that my solutions satisfy the equations. If they don't, algebra is the problem. If they do, the physics is the actual problem. Does that make sense? So it's sort of a binary search on where my error is. Tomorrow we'll take a look at matrix methods, and we'll also look at a couple more tension problems and stuff. Okay? See you.